I would like first to thank the organizer for giving me the opportunity to talk about a modern X-ray home source. So I'd like first to introduce Newcastle University team. So I'm the X-ray facility managers, and the main structural biology laboratory are the following. So we are all in the Faculty of Medical Sciences. So Bert Vandenberg is interested in membrane structural biology. John Marswright is looking at structural studies of metabolic compartmentalization in bacteria. Paula Salgado is looking into structural microbiology of C. difficile pathogenicity. And Wyatt Hugh, who joined us already probably 2 years ago, is interested in human rare disease. And in the Translational and Clinical Research Institute, Jane Endicott is doing mechanistic studies of complexes controlling the cell cycle and transcription. And Martin Noble is looking at biomolecular structure and anti-cancer drug discovery. And a quick remark about all the group. Maybe 3 years ago, 95% of their main structural biology technique was X-ray, protein crystallography. Nowadays, they're probably all more like 50-50 from X-ray to cryo-EM. So it's quite an interesting change. And so there are many other labs using the facility. And part of my job is actually to solve the first problem and build a PDB model for them. So we, of course, do use diamond, and here are few rhetorical questions. So indeed, not all the data are usable. There are duplicates of the sample we set at diamond, and there's also a waiting time. So what I mean is, if you're not familiar to the way a synchrotron operates, they do have a shutdown time in light yellow on this calendar, which is the operational calendar of Diamond for 2023. So users can use the days in blue. Also, if you are doing IP-sensitive data collection, you would have to pay for time if you don't want your data to be released for the public. And but the main point about being efficient and fast is drug discovery development. So the sooner you feed back the result to the chemist, the more likely you will use their time efficiently. There are two main manufacturer of home source. We have been users of Rigaku for years, and we switch with our new source to Bruker. So if you're not familiar to modern sources, that's how they look. So in the enclosure, we get the sample viewer. There is also the robot, which is in this case is called Scout. So this is the sample changer. As well, a bunch of controlling equipment for the cryostream, for example. And the source on this slide is this white box. The detector is in the background. And there's also a CCTV camera to be able to follow the experiment remotely. Here is a close-up of the diffractometer. So, of course, we have a cryostream, beam stop, the collimator. The optics are in the background there. We have a sample camera to be able to center the crystal remotely. Dryer for the robot in the front. Again, the detector. We can move, of course, the distance, but because home source detectors are quite small, we have also a 2 theta angle, which allows to offset the detector to catch high resolution reflections. And of course, we have a bunch of angles, so omega, we tend to use phi for data collection, and kappa. So I've taken the video from Exilum, who makes the metal jet. So a typical way of making X-ray is to use a high current on a copper target. So in this case, it's a fixed target, but popular technology is to have a rotating anode. So in blue are electrons, and in green are the X-ray generated. And so you will generate heat, and so which is limiting the current you can use So higher current will generate more X-ray. So Excelum had the idea to use a liquid metal, which is gallium. And basically, it's like an inkjet printer. You replace the metal quite quickly, so you can use higher current to get more X-ray. So of course, we were wondering, so here I represented the anomalous term for sulphur. So we were wondering, gallium, Ga on the graph, is slightly less favorable for anomalous signal of sulphur. In comparison, you have the tunable beamline IO3, IO4, I24 represented, as well as the low energy beamline I23. So it was a concern. And here I couldn't resist finding one of those videos on YouTube about this little Lego guy made of gallium. And around 30 degrees, it becomes liquid metal. So it reminds us of mercury, but gallium is actually not harmful at all. It just sticks everywhere. It's quite dangerous with aluminum. So you can find plenty of videos with aluminum cans and the effect on gallium on them. And basically it will dissolve the aluminum. So it's quite problematic to transport this type of source and gallium on a plane. It's quite dangerous. So I would like to thank a lot Professor Elspeth Garman for coming to Newcastle and bringing Pico ammeter. And using a calibrated pin diode, we were able to measure how brilliant was the source. So this is to measure how many photons the source is generating. And we got a value of 3.3 10 to the 9 photons per second. And at the time, IO4 was at 3.5, 10 to the 11th photons per second. So we were 2 orders of magnitude below, which is not bad at all. But diamond synchrotron is a brilliant source, a brilliant synchrotron, pun intended. And in July, they did upgrade the source on IO41, and it's now at 3.8, 10 to the 12 photon per second. So we are now 3 orders of magnitude below. Sample handling. So of course, if you have a home source, you can really try to optimize your sample handling. So to reduce radiation damage, as you've heard, we collect data at 100 Kelvin. So I always tell users we're not in a business of solving the structure of ice. So to avoid ice formation, we use, of course, small molecules such as PEG, ethylene glycol, but also we often use paratonel oil, which is a slightly different technique where you would replace, well, you would cover your crystal with oil to avoid dehydration. But this requires practice to be successful with it. And we use a lot saturated salt solutions. And they can be quite useful also because sometimes they dehydrate your unicell and you can get a better lattice. And I had to talk about glycerol because in my opinion, this is not a good cryoprotectant. Glycerol solubilized protein, that's why many people use it on a gel filtration, and you may not want to dissolve your crystal. As well, it's a mimic of carbohydrate, so it will stick everywhere and possibly in your active pocket. So yeah, I would not use glycerol. Just a quick mount, we use are exactly the same as synchrotron. So Mitigen loops are made of Kapton. It's X-ray transparent, but it's very fragile. Usually we use them a couple of times and then they tend to break. The Hampton loop are very robust. They're made of nylon, and nylon is not X-ray transparent. So you get a bit of shadow, but it's usually not a major problem. And of course we use the puck system as well. So I just wanted to give you the message. It may spend weeks, months of cloning, purifying, and getting those crystals. You really want to handle them properly. It's often critical. You really want to handle them properly for data collection. So here is a video of the sample changer. Nothing special, but so I'm in a background of the movie, but I could very well have been at home while loading the sample. So basically the sample changer is enabling remote control of the machine for data collection. It takes about 40 seconds to load the sample, and the sample is only 7 seconds out of liquid nitrogen. So that's it. It's gonna go to the goniometer head. And voila. And here is just a short video to show that indeed, so this I've done it from home where I can remotely center the loop. So in this case, it's a mitigen loop, which is empty. There is no sample. So usually we choose the center of the loop, one click. It will move to the center and then turns 90 degrees. So if you've been collecting data at synchrotron, it's exactly the same process. So what we all like is a very nice protein diffraction pattern. The circle on the side is at 1.7 angstrom. And so here we were able to collect a full data set at 1.6 angstrom in 6 minutes. Probably this would be about 20 seconds at synchrotron to give you an idea. And of course, we can use the machine to see, you've seen earlier as well, a salt diffraction pattern. So it's quite different. So it's quite easy to eliminate salts, to not collect them at synchrotron. And ice rings. So here is a bad case of ice ring. Those rings coming from ice on top of your protein diffraction. And the software will not be able to discriminate what signal comes from the protein and what signal comes from water. So you will lose a lot of information. If as well you get a crystal, ice crystal growing in your protein lattice, you may actually break your resolution to around 3.5 angstroms. So again, try to be nice to your samples. So we use the source to prepare the samples, to screen the samples. So right before Christmas, I had a bit of time to do some wet lab, and I just got those crystals after New Year. And so, of course, the take-home message is never judge a book by its cover. Those crystals looks absolutely fantastic, nice hexagonal cylinder. But here is the diffraction pattern. That was 1 minute, which is very long exposure. And basically, we can barely see 2 or 3 spots in the center. Those crystals do not diffract. And we, of course, collect full data sets. So here is an example of sulphur SAD. So experimental phasing is not so much critical these days with Alphafold and Robetta fold. But collecting a good anomalous signal can be quite useful to identify, for example, ligands. So in this case, you have in green the protein C-alpha trace, and the orange blobs are the position of sulfur. So we published this in 2016. It took 62 hours to collect the data on a Rigaku Micromax 007 with a rotating copper anode. To be fair, the Rigaku machine was probably early 2000 design. And so I've been able to get the similar crystals when we got the metal jet. And in this case, in 2 hours data collection, we got a better resolution and the same or similar multiplicity. And I was able to solve the phase problem doing sulfur SAD. So the yellow mesh is the anomalous signal around the sulfur atom. So we also use our home source for drug discovery. This is a project with Jess Watt and Matt Martin in the lab of Martin Noble. And basically, again, the idea is to give really fast the crystallographic results to the chemist so they can synthesize drugs efficiently. So we had 113 samples tested. The resolution range were 1.7 to 2.2 angstrom, and it's quite enough to actually know if you have a ligand bound or not. Just as an example, I represented a blue electron density mesh around the tyrosine, and you can see the data of the map are quite good. The quality of the map is quite good. So I've been pushing the collection to as fast as 3 minutes to collect a full data set to 1.6 angstrom again. And in this case, doing a rotation on 180 degrees. I tried for 1 second exposure for half a degree. And I tried the same with half a second for half a degree, but for 360 degrees, so to get a higher multiplicity. But then the resolution was a bit less, so it was the same sample. So meaning in this case, I was reaching the limit of the system. So for drug discovery, so this is a project with the Yimin under the supervision of Matt Martin in the lab of Mike Waring and Martin Noble. And so for drug discovery, you could screen small molecule libraries, but you would have 10 of thousands, 100 of thousands of molecules or more compounds. So it's quite a daunting task to screen those drugs. So instead, the approach is a fragment library, where basically you get building blocks, if you wish, bound to your drug target, and you hope then to grow and link those building blocks later on. The problem with small fragments is they have very low affinities, and they can be quite hard then to identify on with X-ray diffraction. So the idea they had, so Mike Waring and Martin Noble had, was to have a halogen atom within the fragment. And the idea is to use, once again, the anomalous signal to actually identify the ligand in the diffraction, in electron density. And that's just the difference, again, of signal between copper and gallium. So Yimin grew 2 different targets, and you can see on the right-hand side again, representative electron density around tyrosine. So the data collected was quite good. The top one is slightly higher resolution. You can see a hole and blobby around the tyrosine, whereas the bottom one is, you can see the hole. So the frag lights were soaked for 48 to 72 hours. And the data sets of the APO forms were 1.5 or 2 and 2 angstrom respectively for the targets. And the data collected was exactly in the same range. So it was a 30% hit rate, which is in case it's quite high. And they identified 3 and 4 sites respectively. So then the future work when you work with fragments is to then grow, link them, and to try to get a drug candidate. So in conclusion, we use our home source in conjunction with synchrotron. We of course use a lot diamond. It allows us to advance the project faster. As well, we can send very well prepared the sample to diamond. It's an invaluable tool for training on sample handling. So again, really, would like to make the point, you're spending a lot of time getting those crystals. You should try to handle them the best you can. It drives drugs discovery efficiently, and SAT phasing can be done painlessly. But of course, nowadays it's less critical, but yet the anomalous signal can be quite useful. The future work would be to decouple the software. So currently data collection is done after, so processing of data is done after data collection, and nothing is happening when we use the automated mode until the processing is finished. We are working on our local graphical user interface, which is pretty much looking like GDR. and plate screening software is missing. So the MetalJet from Bruker and Rigaku was a similar system, but from Bruker you can screen plate, in situ plate, but the software is lacking. So I would like to acknowledge my previous line manager, Rick Lewis, who hired me, and my current line manager, Bert Vandenberg. As well, all the groups in 22 using the facility. And Bruker, who's been really good communicating. And finally, the founders. And you for your attention. Thank you.